Hello, my name is Dr. William Benzing, and I'd like to present to you a PowerPoint presentation entitled The Hydrogen Exploration Strategy. The strategy gets geological revelation from the biblical scripture, Job 28, verse 9, geochemical revelation from the mineral magnetite, and geophysical revelation from gravity data. The presentation is about 35 minutes long. The presentation ends with a description of a novel prospect in Oklahoma called the Smoking Gun Prospect, which should provide a spindle-top moment for hydrogen exploration. Currently, the entire world is looking to drill a significant and sustainable hydrogen well that is economically viable. I believe this prospect can deliver such a well. I also believe that the well will serve as an exploration template for other hydrogen wells around the world. I'm a semi-retired exploration geophysicist living in Tulsa. I own no acreage position in the prospect. I am looking for a company to drill the prospect. My interest is ensuring the truth and wisdom of God's Word. I'll be glad to serve as a technical advisor in the drilling of the well. God says it is the glory of God to conceal a matter, but the glory of kings to search out a matter. Join me as I reveal a strategy for locating geologic hydrogen. Thank you.
Hello, my name is William Benzing and I am excited to present to you a hydrogen exploration strategy based upon the premise that in the beginning, God created the heavens and the earth. The strategy utilizes 1. A structural geology concept inspired by the book of Job chapter 28 verse 9, 2. Magnetite revelations related to hydrogen generation, and 3. How to detect a shallow, uniquely shaped hydrogen reservoir using gravity data. The next overhead lists the presentation topics. This overhead lists the hydrogen topics, keywords, and strategic information gained in this presentation. Beginning with the topic geology, the following keywords will be mentioned, namely, buried mountains, subgranite, biblical Job 28 verse 9, structural modeling, uplift and ductile shearing, and structural closure and sealing. The strategic information gained is where to explore for subsurface hydrogen reservoirs. Concerning the topic of geochemistry, keywords are hydrogen generation, iron-rich dolomite and magnetite. The strategic information related to geochemistry is to verify the presence of a hydrogen source rock. Regarding geophysics, residual gravity data and horizontal component will be mentioned for the purpose of direct detection of a hydrogen reservoir. Finally, aspects of the Smoking Gun hydrogen prospect will be discussed for the purpose of finding a company to drill the prospect. Buried mountains occur when deep, crustal rocks are thrust upward in a wedge shape to form a high in the igneous basement rocks. Based upon mud gas analysis from oil and gas wells, hydrogen accumulations exist in sedimentary rock around uplifted, buried mountains. Because of the extremely low density of the hydrogen, the gas migrates upward to the crest of the uplift. Currently, companies like Hytera are acquiring acreage and exploring for hydrogen along uplifted mountain crests in Kansas. The Smoking Gun prospect proposed in this presentation also lies along the crest of a basement uplift in southwest Oklahoma. Whereas Hytera is looking for reservoirs that are sealed by low permeability shales and evaporites. The Smoking Gun prospect is a subgranite play sealed by a thin, extremely low permeability, granite caprock. As shown, the Job 28-9 exploration strategy predicts a low-lying, recumbent fold, structural trap. The conventional interpretation, on the bottom left, suggests no structural trapping on the backside of the uplift. However, the unconventional, biblical interpretation, based on Job 28 verse 9, predicts the presence of the recumbent fold trap. How the trap is formed will be discussed next. The photograph shown in this overhead shows the complexly folded, internal structure of an uplifted mountain. The structural modeling described in this presentation explains how the complexity is formed based upon Job 28:9. Job 28:9 states he puts forth his hand upon the rock, he overturns the mountains by the root. Okay, what is the geologic revelation here? The scripture reveals there are two stages of mountain building, an initial mountain building stage followed by a combined uplift and rotation stage which overturns the mountain. The two stages are depicted using the geologic cross-sections shown, namely, Stage 1 mountain building and Stage 2 uplift and rotation. It is Stage 2 that turns the gentle folding in Stage 1 into the complex folding like that observed in the earlier buried mountain photograph. Let's consider the geologic forces suggested by Job 28:9. The Stage 1 forces produce surface folding in the crust most likely by wrench tectonics using compressive, lateral forces. In Stage 2, the pre-existing surface folds are uplifted and overturned by inclined, deep mantle forces with the rocks deformed by a rheology called ductile shearing. The wavelength of the Stage 1 surface folding, combined with the shape of the uplift and shearing angle determines the complexity of the final mountain folding. Given the same shear angle shown in blue and uplift grid shape shown in red, this overhead displays how these factors combined with pre-uplift fold wavelength determine the complexity of the post-uplift mountain structure. Notice that as the fold wavelength gets shorter, the complexity of the mountain structure increases. Of significance is the observation that at short wavelengths both high-angle frontal thrusts and low-angle back thrusts are formed. Although not shown here, the low-angle back thrusts can be formed into flat-lying, recumbent folds capable of structurally trapping hydrocarbons and possibly hydrogen. It is this unique structural trap that traps geologic hydrogen in the smoking gun hydrogen prospect that will be discussed later. During structural modeling, it is important to maintain rock volume during the deformation process. As shown in this overhead, using the graphical uplift grid method, based on ductile shearing, preserves rock volume, or in two dimensions, the area. In the upper figure, the preserved areas are shown before and after uplift. The areas are preserved by thickening and thinning the uplifted material. The pre- and post-geologic sections at the bottom of the figure have equal areas. Please note the recumbent fold that is formed on the backside of the uplift. It is this counterclockwise rotated fold that will eventually become a structural trap for hydrogen. Before the geology discussion is finished and we discuss geochemistry, I would like to show how, in a video, a transpressional, pre-uplift wrench fold is uplifted by ductile shearing to form a structural gas trap with a gas over water contact. This mechanical modeling method simulates the graphical method of modeling just shown. It shows how to form a slightly recumbent, transpressional fold into a flat, low-lying recumbent fold using crustal uplift combined with ductile shearing. The final fold strongly resembles the large-scale, flat-lying, recumbent fold observed in Greenland. In Greenland, the upper limb of the fold has been unconformably eroded. The height of the fold in the photograph is estimated to be about 2,500 feet. Let's take a closer look at the structural closure on the underside of the flat-lying recumbent fold. A horizontal gas-water contact, shown in red, has been added to the underside of the fold. Assuming the core of the recumbent fold is made of an impermeable material like granite, the shape of the gas reservoir, beneath the caprock, is similar to an airplane wing, with a thick leading edge and a tapered trailing edge. As will be shown later, during the geophysics discussion, this gas reservoir shape can be used to directly detect the gas reservoir using specially processed gravity data. This concludes the geology discussion, having shown how a unique structural trap could be formed on the unexplored backside of a buried mountain. In the geochemical discussion, which is presented next, a hydrogen gas source is proposed that will fill the structural closure just presented. In 2004, I participated in the drilling of a 7,000-foot wildcat well to test the presence of a hydrocarbon reservoir underneath a low-lying, recumbent fold in the buried, Wichita Mountains of southwest Oklahoma. Unfortunately, the well was drilled in a down-dip, off-structure location. Several porous zones in the iron-rich dolomite were tested by swabbing formation fluid. The swabbing produced black salt water but no commercial hydrocarbons. Given time, the swabbing water cleared up, leaving a layer of black sediment in the bottom of the drill pit. The black sediment was determined to be magnetite, the only naturally magnetic mineral in the earth. After shutting the well in, a weak, almost colorless, gas flare was noticed at the wellhead. Further analysis determined the magnetite crystals to be nano-sized. The presence of dispersed nanomagnetite crystals moving through the porosity of a dolomite rock puzzled me for many years. Some 20 years later, thanks to the recent interest in hydrogen exploration, I have a scientific explanation for the presence of the nanomagnetite in the drill pit. Within the last decade, scientific studies have indicated that the interaction of iron-rich minerals like olivine and dolomite with subsurface water can produce natural hydrogen, and the presence of magnetite can act as a catalyst in the reaction. Further geochemical research confirms the magnetite is more than just a catalyst in the reaction, it is the primary source of the hydrogen. Quoting from the paper entitled Reassessing the Role of Magnetite During Natural Hydrogen Generation, it states the following. As for the future of native hydrogen exploration, these results demonstrate that magnetite lithologies should be targeted while exploring natural hydrogen resources. Can nanomagnetite be formed in the porosity space of an iron-rich dolomite like anchorite? Yes. This process is known as diagenetic magnetite formation, meaning it occurs after initial deposition of the sediment and during the burial and alteration of the rock. This has been verified by a paper entitled, Formation of Magnetic Nanoparticles by Thermal Decomposition of Iron-Bearing Carbonates, Implications for the Evidence of Fossil Life on Mars by Alicia Cohen. In her paper, she displays an SEM photograph of magnetite nanoparticles that have formed on the surface of iron-rich dolomite. The cluster of magnetite nanoparticles appears white when using a scanning electron microscope. Because there is no preferred magnetic orientation in the particle cluster, the particles are weakly held together and easily broken apart during swabbing of the well. Based on the previous geochemistry discussion, the entire iron-bearing dolomite can contain nanomagnetite in the porosity which can source hydrogen at low temperatures. Consequently, as shown in this overhead, the dolomite source rock can become a migration pathway to a dolomite reservoir. If so, an off-structure, down-dip well that exhibits nanomagnetite when swabbed can be used as an indication to look up-dip for a hydrogen reservoir. This concludes the geochemistry discussion. In the next geophysical discussion, it will be shown how to locate a low-angle, recumbent fold, structural trap using gravity data. In this discussion, I would like to explain the geophysical strategy used to locate hydrogen reservoirs trapped underneath a low-angle, recumbent fold concept that was shown earlier in the geology discussion. During that discussion, it was shown how a two-dimensional, wing-shaped structural closure was formed. The unique shape of the closure was a result of low-angle uplift and ductile shearing. This two-dimensional shape was derived from a cross-sectional slice taken across a pre-uplift, transpressional wrench fold which is depicted in the next overhead and displayed in green. The propeller shape of the transpressional fold before uplift is typical of a wrench fold created by lateral shearing and compressive crustal forces. The propeller shape is due to the slightly recumbent shape changing direction along the fold crest. Using the additional, yellow, cross-sections, and uplifting the entire fold on the backside of a low-angle uplift, map views were drawn of the before and after uplift structures. The propeller shape of the before uplift fold is clearly seen in this map view. The location of the green cross-section, where maximum recumbency and structural closure occurs, is shown for both maps. The extent of the structural closure beneath the fold is outlined in red. As shown in the next overhead, the overall closure shape beneath the fold was determined to be triangular in shape, pointing in a down-dip direction. In this overhead, the modeled structural map has been rotated so that the down-dip direction points south. Below the map, 3 large-scale cross-sections are displayed, 1 dip and 2 strike cross-sections. The lateral closure extent is indicated in red. Also shown, in close-up, expanded view, are color-coded cross-sections, through the hidden closure which indicate vertical closure thickness. The thickest portion of the reservoir is shown as number 4 in blue. Notice that the unique closure shape creates a symmetrical color band in the strike direction and an asymmetrical color band in the wing-shaped, dip direction. When the color-coded thicknesses are drawn on a map, the mapped closure area looks triangular but is elongated in the dip direction. Knowing the reservoir shape, the next overhead shows how gravity data can be utilized to locate the unique shape of the hydrogen reservoir. Based on the wing-shaped structural reservoir model in the dip direction, a gravity model was constructed for a shallow, wing-shaped, low-density object. The vertical gravity data was measured above the ground surface in milligaules. The horizontal gravity gradient was then calculated for a uniformly spaced measurement interval along the gravity profile in units of milligaules per meter. Rapidly changing gradient values occur up-dip where the wing-shaped reservoir exhibits the greatest curvature. As shown, a minimum in the horizontal gradient occurs where the reservoir is thickest, in the blue portion of the reservoir. Continuing down dip, along the trailing edge of the wing-shaped reservoir, the horizontal gradient value increases as the amount of low-density material diminishes. Because of the shape of the reservoir, a unique gravity signature, using horizontal gradient data, should be able to detect the shallow hydrogen reservoir on the backside of a buried mountain. The unique gravity signature, as displayed in map view, is shown in the next overhead. The hydrogen exploration strategy based on geophysics says that when exploring for hydrogen on the backside of a buried mountain, first, collect Bouguer gravity data. Next, process the data to produce a map of the horizontal gravity gradient. A stretched-out, triangular-shaped, anomaly signature which points in the direction of geologic dip is a direct indicator of a buried, low-density gas reservoir. If nanomagnetite has been seen in dolomitic rocks down dip of the anomaly, the gas reservoir should have a high percentage of hydrogen and possibly helium. For the remainder of this presentation, I would like to present the Smoking Gun Hydrogen Prospect in southwest Oklahoma. The prospect exhibits the geology, geochemistry, and geophysics strategies that have been discussed in this presentation.
Is nanomagnetite the smoking gun that can be used to locate shallow, white hydrogen in the earth? Let's drill and find out. Let me explain. Because of the increased interest in geologic hydrogen, which is also called white hydrogen, the United States Geologic Survey has published in 2025 a map of potential for finding geologic hydrogen in the United States. The map shown here is color-coded in blue and based on the likelihood of drilling a successful hydrogen well, with the dark blue signifying the greatest median prospectivity, which is a 50% chance. Notice the Smoking Gun Prospect lies in the dark blue trend which cuts across southwest Oklahoma. This is a simplified, north-south geologic cross-section across the Wichita Uplift in the vicinity of the Smoking Gun Prospect. The uplifted granite and basalt basement rocks, shown in pink and orange, are thrust upward and eroded at an angle. This creates a thick, 40,000-foot sedimentary section on the front or north side of the uplift and a thinner section on the back side or south side of the uplift. The Smoking Gun Prospect lies on the back side of the uplift, adjacent to the shallow, Hollis Basin.
The geologic strategy for hunting hydrogen is to look on the back side of uplifted, buried mountains. This was the result of geologic, structural modeling based on uplift combined with the rock deforming by ductile shearing. The modeling is shown at the bottom of this overhead. Above it is an expanded view of the Smoking Gun Hydrogen Prospect. Please note that in these sections, hydrogen gas is shown in green, not blue. The green in the iron-rich carbonate means the rock serves three purposes. It is a hydrogen source rock, a migration pathway and a trapped, reservoir rock. This will be discussed next in the geochemical strategy of the prospect. The approximately 1,500-foot hydrogen reservoir can be penetrated by drilling a test hole through 1,900 feet of Permian sediments and several thousand feet of granite. As mentioned earlier in the geology exploration strategy, I was involved with drilling a down-dip, off-structure well that produced nanomagnetite from porous and permeable zones in the Arbuckle Dolomite. The down-dip, dry hole is shown in the cross-section. Copious amounts of nano, in the range of 5 grams per gallon of swabbed brine were produced. Using magnets, the nanomagnetite was separated from the brine as shown in the overhead. The following question was addressed in recent geochemical research in Frontiers of Earth Science. In the presence of warm water, which is the best hydrogen generator, iron-rich granite, olivine or magnetite? The answer is, based on laboratory experimentation. Lower temperature magnetite significantly outperforms iron-rich granite and olivine in terms of hydrogen production. The bar graph clearly shows this outperformance in hydrogen production. This is the geochemical strategy for hydrogen exploration stated earlier in this presentation. If nanomagnetite is present in swabbed, dolomitic formations and the well is non-productive but with a weak, blue flame when tested, explore updip for structurally closed hydrogen production. I believe the most compelling evidence for the presence of subsurface hydrogen is the presence of a unique gravitational anomaly on the backside of the buried mountain. The Smoking Gun prospect clearly shows this anomaly, which may become a direct hydrogen indicator for hydrogen reservoirs. The Smoking Gun hydrogen prospect geophysical strategy is to use gravity data to locate hydrogen reservoirs in flat-lying recumbent folds which are formed on the backside of buried mountains. This overhead shows two maps of the United States. The Bugey gravity map on top shows the location of buried mountain ranges where dense basement rock has been uplifted to create a stronger gravitational attraction in pink. The bottom map is the United States Geological Survey map of hydrogen prospectivity with the greatest likelihood of finding hydrogen shown in dark blue. The correlation of pink and dark blue areas is obvious. You find hydrogen along buried mountain ranges. The location of the Smoking Gun prospect in southwest Oklahoma indicates the presence of buried mountain range, namely the Wichita Uplift, and a high probability of finding geologic hydrogen. Let's look at a gravity model across the prospect. Using the geologic cross-section of the Smoking Gun prospect, a gravity model was created for a low-density, wing-shaped object buried in a higher-density matrix. The gravity profile shown below the cross-section displays the horizontal gravity gradient derived from the Bugey gravity data. With a flat, gas-water contact, the horizontal gradient data is sensitive to the slope of the reservoir caprock. For a wing-shaped reservoir, the slope is lowest where the reservoir is thickest. Also, because of the wing shape, the gradient values get stretched out in the down-dip direction. As shown earlier, during the geophysical discussion of gravity modeling and geologic structure, the map views of reservoir thickness and the model of horizontal gravity gradient should be very similar in shape and direction. The Smoking Gun hydrogen prospect displays a unique gravity anomaly that supports the presence of hydrogen reservoir. This gravity data was acquired over the Wichita Uplift and published in the Oklahoma Geologic Survey Guidebook No. 38. On the left is the residual Bugey gravity map. The Wichita Uplift is easily identified in northern Greer County by a continuous purple color signifying a strong positive gravity which is normal for dense, igneous basement rock. On the right, the horizontal gradient map, which is calculated from the residual Bugey gravity map, is shown. The horizontal gradient map is used to highlight small changes in rock density. There is an obvious anomaly associated with the gradient map signifying a very low gradient value within the anomaly, which is similar to the gravity model just shown. In addition, the gradient values are stretched out in the direction of geologic dip, in agreement with the gravity modeling. Finally, based on uplift, structural modeling, the triangular shape of the anomaly is to be expected for an overturned, transpressional fold. These observations suggest that the anomaly can be explained by a shallow, hydrogen reservoir capped by the thin granite caprock. This overhead summarizes geological, geochemical and geophysical data concerning the smoking gun hydrogen prospect. Geologically, the hydrogen is trapped under a low-lying, recumbent fold sealed by a thin granite caprock. Geochemically, the hydrogen is produced from nanomagnetite within the pore space of the Arbuckle dolomite, which migrates upward, into the reservoir. Geophysically, the exact location of the shallow reservoir can be detected based on the shape and orientation of a gravity anomaly. A comparison between the field data anomaly and the modeled anomaly is shown in the next overhead. This overhead shows a comparison between the shape and orientation of the gravity anomaly, on the left, and the modeled hydrogen reservoir thickness on the right. The color agreement was artificially made, and the 5 colors shown in the gravity anomaly were used to make 5 reservoir thicknesses measured from the base of the granite seal and the flat, gas/water contact. The location of the thickest part of the reservoir is shown in blue. This location corresponds to the lowest horizontal gradient value, also shown in blue. If this geophysical interpretation proves to be correct, the gravity signature could be a template for further hydrogen exploration along the unexplored backside of buried mountains around the world. This reminds me of using seismic bright spot signatures used to locate trapped, methane gas reservoirs in the Gulf of Mexico. As mentioned earlier in this presentation, shallow and abandoned, Permian, natural gas fields, located above the granite seal, should be located above the structural high created by the wing-shaped reservoir. The next slide verifies this statement. Abandoned, Permian, brown dolomite and granite wash oil and gas fields above granite are shown in this overhead. This distribution of fields supports the location of the subgranite, structural high which traps the hydrogen gas. The last slide in this presentation estimates recoverable hydrogen reserves associated with the smoking gun prospect. Given a reservoir shape similar to a rectangular pyramid with dimensions shown on the far right and recovery assumption at the bottom, the estimated recoverable reserves are 53 BCF of hydrogen. Based on an AI overview estimate that 1 BCF of hydrogen has a value of $5 to $10 million, 53 BCF of hydrogen has a value of $265 to $530 million.